I want to perform an example of solving a system of two linear equations. It may look something like this. I know that they're linear because all that's happening to x and y is that they're being multiplied by real numbers, and the only other thing around are constants. So there's no sine x, there's no square root of y, there's no x times y squared. It's linear in x and it's linear in y. I'd like to be able to figure out the value of x and the value of y that makes both of these equations come true simultaneously. There are lots of solutions to this equation, and there are lots of solutions to this one. But in fact, there will only be the one solution to both of these equations. What can I do to determine that solution? I am allowed, when I have an equation, to multiply both sides of that equation by whatever I want. I know it will stay true. If 5 equals 5, I know that 3 times 5 has to equal 3 times 5. That's the power that I'm going to use in this problem. I'm going to selectively, judiciously choose the right number to multiply both sides of my first equation, and then possibly a different number to multiply both sides of my second equation. And after I'm done, you'll realize why it is I chose those numbers. And there's lots of choices I have, but here's one. What if I were to multiply the top equation, both sides, by the number 3? If I did, I would get this result. 6x plus 3y is 21. If this equation is true, that equation has just as much information and it's just as true. This equation, I'm going to multiply by 2, both sides. 2 times 3x gives me 6x. 2 times negative 2y gives me negative 4y, and 2 times 1 is 2. The next power that I have with equations is that I can add equations that are true. So if 5 equals 5 and 7 equals 7, then yeah, 12 equals 12. And that's what I'm going to do here, only it's not quite adding them because 6x plus 6x would give me 12x, and 3y plus negative 4y would give me negative y, and it feels like I haven't really made any progress. I still have an equation with both of my letters in it. I mean, secretly, my goal from the beginning was an equation that only has one letter in it because I know how to solve those. It doesn't seem too hard to realize that were I to subtract these two equations, then in fact 6x minus 6x would eliminate the x entirely from the question. And if 7 equals 7 and 5 equals 5, then sure enough, 2 equals 2. I can subtract equations and be guaranteed that the subtracted equation is true. That's what I'm going to do. I'm going to subtract this equation from this one. 6x minus 6x, there's nothing, 0. I won't even write it. 3y minus negative 4y, that's 7y. 21 minus 2, that's 19. This is an amazing advance on what I had before. I just have a single equation and a single unknown. I can solve that immediately. I should divide both sides by 7. I now know what y is. It's 19/7. The only thing left for me to do is to determine x. I can go back to any of these equations, the one most convenient to me, to figure out what x is. Maybe I choose this one. Why? Because it's the one that involves the least amount of work in substituting y. If I substituted 19/7 into this equation, then I'd have this moment of multiplying by negative 2, and I don't feel like doing that. But I can substitute 19/7 into either one of these, and I'll know I'll be finding x correctly. So let's do it into this one. Maybe I put an arrow to help the reader. 2x plus 19 over 7 equals 1. No, not 1. This is the number 7. And then I want to solve for x, so I want to bring the 19/7 over to the other side. So let's do that. 2x has to equal this thing minus 19 over 7. Well, I know that I'm subtracting fractions here. Why don't I write 7 as something over 7? 49 over 7 will do the trick, because 49 over 7 really is 7. And now I subtract the 19 over 7. This tells me that 2x is 30 over 7. But I didn't want 2x, I wanted x. So I divide both sides by 2, and I learned that x is 15 over 7. This method gets called elimination.